All right, let's get into Gauss's law. And before we really talk about Gauss's law, I need to define a quantity called flux. In this case, we're going to look at the electric flux. The symbol for flux looks like that. And how you find electric flux is that you accumulate the E field over space. Okay, so this is the electric field accumulating it over all the surface area of some three-dimensional object, and that's the flux. Well, why is that the flux? Well, let's define what the flux is. The flux is the number of field lines, that penetrate a surface. So you can have positive flux or you can have negative flux, and it kind of just depends what's happening. And here's Gauss's law. What Gauss said was that the electric flux is equal to the charge enclosed divided by epsilon naught. And epsilon naught is our friend, and again, epsilon naught, I never even keep track of what epsilon naught is, because what I know is that K is 1 over 4 pi epsilon naught, K being Coulomb's constant, which is 9 times 10 to the 9th. So if you wanted to find epsilon naught, then epsilon naught is just 1 over 4 pi times this. So it's some really small value. Okay, so going back to Gauss's law, this is what it says. It says that this quantity, which is the electric flux, which is the number of field lines that penetrate a surface, is equal to the charge enclosed. Well, it's actually proportional to the charge enclosed. Okay, so let's go through Gauss's law, and we'll do a bunch of examples of why we would use this. And really remember, we use Gauss's law to do what? To find the E field as some function of R. Right? That's our goal, to find E field. Now again, we don't usually use function notation in physics. We just say E equals, but all of these electric fields will be functions of R. Okay? So let's just do our first example, some point charge. Some point charge. So it's just some charge located in space. We'll make it a positive charge. And I want to know the E field at a distance R from it. So what's the E field here, or here, or here, or here? Now, we know that the E field is going to go spherically outward from there, but what's the formula? Now, you may have already memorized it from your statics, but let's use Gauss's law to derive what we already know. And so what Gauss's law says is that we take a Gaussian surface. In this case, we're going to use a sphere, which is our hypothetical three-dimensional surface, and we're going to take this and surround that charge. So imagine that this charge is in the middle of this Gaussian sphere. Again, this Gaussian surface in this case is we're going to use a sphere. And we're not always going to use a sphere, but we're going to use a sphere in this case. And what we're going to do is our Gaussian surface is going to involve this dA. Now, when you look at Gauss's law, we're going to say that E dot dA is equal to the charge enclosed over epsilon naught. Now, if you look at my Gaussian surface, it's placed in a way that it's symmetric. All the areas, all these little bitty dAs, right? That little spot of area on that Gaussian sphere, it's got some flux that goes through it, right? See, that field line is going to go through that. However, since my sphere is symmetrically placed around this charge, all of the E field is the exact same value everywhere on that red sphere. So that E field can actually come out of the integral. The integral of dA is just the area of my Gaussian sphere, which is 4 pi r squared. The charge enclosed is just that Q, that charge, over epsilon naught, and then I can solve for the E field. And I get E equals Q over 4 pi epsilon naught r squared, and we know that 1 over 4 pi epsilon naught is K, and we get KQ over r squared. Again, this is probably the formula that you already have memorized for the electric field due to a point charge, and you can see it's a 1 over r squared. KQ 1 over r squared. So the E field is a function of r, and it falls off like an inverse square law. Okay, and this is that kind of setup we use. We use Gauss's law to find the E field due to random charge distributions. we put a Gaussian surface, and again, this Gaussian surface has a radius of r, but all the parts of this are all at that same r value, and so the E field can be factored out, and we're going to do that every single time. Okay, let's do a infinite line of charge. We'll fit it down here. An infinite line of charge. Okay, so imagine this is some wire, and it's an infinite wire, right? They call that a really long wire. And I want to find the E field, let's say right there, a distance whatever away. So what we're going to do is we're going to put a Gaussian surface around it, and in this case we're going to put a cylinder. Right, that cylinder is some random r. And here's kind of the hard part with an infinite line of charge. So write down Gauss's law. E dot dA equals the charge enclosed over epsilon naught. Okay, now the A. If you think about the E field is going to go like this, right? It's going to go out. And some of the E field is going to go this way. But then, like that part, but then stuff over here is going to go this way. And hopefully you're okay with the fact that there's all going to be these things pointing left, but also symmetrical things pointing right. And all the lefts and the right cancel out. I mean, this guy points left, but this guy points to the right. And what you're left with is that the E field, due to this thing, is actually only going outward from this line. Up, down, left, and right from this line. So it's going to go this way, this way, this way, this way, this way. And so the area, if you think about what the flux is, the E field is constant on this surface. The area that we're accumulating here is actually just the wall of the cylinder. I know things go out of the cap, but things go into the cap of our cylinder. The only area that really matters is the surface area that's the wall of our cylinder, and that is 2 pi r L. L being the length of my hypothetical cylinder, right? That's my Gaussian cylinder. It's got a length L. Why L? Because I'm just making it some random L, and you'll see why that goes away. Okay? Then, what do I multiply by? Well, what's the charge enclosed? And this gets back to concepts we've looked at before. If it's an infinite line of charge, we can't say that what have we really enclosed? Well, I don't really know how much, because the whole thing's infinitely big, and I've closed a part of it. However, even an infinite line of charge has some charge density. It's got so many coulombs per meter of charge. Okay? So the charge I've enclosed is some lambda times the amount of charge length I've enclosed, which is in fact L. Again, this distance is so many meters. And I've enclosed how much charge? Well, if you tell me you have so many coulombs per meter, and I multiply by the number of meters, this then, lambda times L, coulombs per meter times meters, gives you the coulombs that you've enclosed. And divide that by epsilon naught, and then you'll see how nice this works out in the fact that the L cancels. It has to cancel. L was some arbitrary length of our Gaussian cylinder. Certainly the E field doesn't depend on L. The E field is going to depend on a couple of things. It's going to depend on lambda, how dense the charge is on your line, and then R, which is how far you are away. So if you solve this for E, you get E equals lambda over 2 pi epsilon naught R, which is fine. You can leave it like that. Or you can write it as, again, if that was a 4, I could multiply top and bottom by 2 and make that 2k lambda over R. The important thing is that we've shown that the electric field due to an infinite line of charge is proportional to 1 over R, whereas a point charge, the E field is proportional to 1 over R squared. They are different. This is an inverse square law, meaning double the distance, you cut the electric field into a quarter. Here, if you double the distance, you cut the field into a half. And again, at this point in your physics career, you should be comfortable looking at the difference between a 1 over an R squared and a 1 over R. And this is what Gauss's law has done for us. It's demonstrated that the electric field due to a point charge and the electric field due to an infinite line of charge are different. And in this case, we've shown that. All right, let's take a look at some other examples, other shapes. Okay, so we have a point charge, we have a line of charge, and now we have some infinite sheet of charge. So this is like how you fake draw some infinite plane, right? And this is some infinite sheet of charge. And hopefully it's that same argument that if you look at, up here, it's going to be pointing left, right, up, down, this way. And if you look at charges down here, well, they're going to be pointing up, down, left, and right. But this one's going to be like pointing this way, and that one's going to be pointing that way, and they're all going to cancel. What you're going to get is the electric field is going to come out of the paper, and then on the other side, they're going to go that way. No net field lines are going to go left or right, because all of these are going to go this way a little bit, but then all of those are going to go that way a little bit, and they're all going to cancel. The Gaussian surface we're going to use is we're going to put a cylinder, and we're going to stick this cylinder right through the sheet. So some of the cylinder is going to be popping out on this side of the sheet, and some of it is going to be going into the sheet. I know, you don't expect me to actually draw this very well, but you can imagine that this cylinder is stuck, and right there, the darkened part, that's where the cylinder goes through the sheet. Okay? And so what do we say? Well, we just write down Gauss's law. E dot dA equals charge enclosed over epsilon naught. The electric field is constant on our Gaussian surface, and again, our Gaussian surface is some cylinder, and that only goes through the caps. Again, the E field is pointing from here straight this way, and on the other side straight that way. No field lines, no net field lines actually go through the wall of the cylinder. This guy would have some that way, but then some this way, and nothing eventually, no net field lines go through the wall of our cylinder, just the caps. And so our area is two circles. And some are going to go through this cap, and some are going to go through that cap. Some are going out of the page, and some are going into the page. The charge enclosed. Well, it's very similar to the last example. When we had a finite line of charge, we needed to use lambda. Here we're going to use sigma. And sigma is charge, coulombs, per square meter. Again, it's still just a charge density. This is some charge density. And so if you take sigma times how much you've enclosed, but again, you've enclosed how much of the sheet has your Gaussian surface enclosed. Well, that's this area right there. And that's just pi r squared. That's how big your Gaussian cylinder is. Okay, and that over epsilon naught. And look how easy this is. Cancel, 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 and you get the electric field is equal to sigma over 2 epsilon naught. And this says, oh my goodness, look at this. The E field is constant. Now remember, our point charge on the previous page, our point charge acted like a 1 over r squared. Our infinite line of charge acted like a 1 over r, and now our infinite sheet is actually a constant, meaning the electric field here and here and here and here, as you move away from the sheet, above the sheet, you go the electric field is always this value. You tell me the total charge and the total area of this big sheet, and then I will tell you the electric field. And that's really nice because it's a uniform field, constant or uniform, and then we can use that in so many ways because it's an easy way to create a uniform electric field. Okay, now let's do a metal sphere. A metal sphere, and when I say metal, I mean it's a conductor. Okay, so we have some metal sphere. Okay, and it's got so much charge on it, charge Q. Okay, so we're interested in two things. What happens if R is less than capital R? Meaning, what's the electric field inside a metal sphere? And you're like, okay, well, make your Gaussian surface. Hopefully it makes sense that if we have a metal sphere that we're going to use a sphere, our Gaussian sphere inside. So we're going to put our Gaussian sphere like there. Okay, and you write down Gauss's law. The accumulation of the E field over that Gaussian surface area is equal to the charge enclosed over epsilon naught. But your knowledge of a conductor says that if you put a charge on a conductor, all the charge is going to go to the surface. There won't be any charge inside. So what have we just proven? Well, if the charge enclosed is equal to 0, so we get E equals 4 pi r squared equals 0 divided by epsilon naught. Well, of course then, that means the E field is 0. And we've just proven that the electric field is 0 everywhere inside a metal sphere. And it'll turn out that it's 0 inside any conductor, because we can do the same kind of thing. Okay? What happens if R is equal or greater than capital R? Well, there's our metal sphere, and now we're interested in the electric field outside of this. So we put our Gaussian surface on the outside, and we write this down again. E dot dA, charge enclosed over epsilon naught. E is constant. The area is 4 pi little r squared, where the little r is bigger than capital R now, capital R being the radius of our sphere. And the charge enclosed is just the whole charge. And as you can see, solving this, you get E equals KQ over R squared. And what we realize is that a metal sphere, if you're on the outside of it, acts just like a point charge. Just like a point charge. We can treat it as if all the charge is located right in the center, and so it's a 1 over r squared, so it's a KQ over r squared. So spheres are really easy. If they're metal, the electric field is 0 inside, and the electric field on the outside is just like it was a point charge. Okay, so we have a point charge, we have an infinite line, we have an infinite sheet, we have a metal sphere, and we can look at the inside on a metal sphere or the outside of a metal sphere. All right, there's only one more thing we have left. I mean, there are other things, but the other main one left is what happens if we have an insulator. Okay, what if we have an insulated sphere? Insulated sphere. Okay, so we have our sphere, except now the charge is uniformly distributed throughout it. So they can give you two ways. They could tell you that Q, the total charge, and they tell you R, or they could give you some charge density rho, and again rho is coulombs per cubic meter, right? It's a three-dimensional charge density, right? So we had lambda, sigma, and now we have rho. These are all interchangeable because if rho is constant, then what is rho? Well, rho is just Q divided by 4/3 pi r cubed. So if they give you Q, you can find rho. If they give you rho, you can find Q. And again, this is assuming that rho is a constant. All right, let's do the easy one first. The easy one is if R is greater than or equal to R. So if our Gaussian sphere is outside, put our Gaussian sphere on the outside. Okay, then Gauss's law says that E dot dA equals the charge enclosed by your Gaussian sphere over epsilon naught, right? The flux is proportional to the charge enclosed, right? The number of field lines is proportional to the charge that you've enclosed inside that sphere. E dot dA is E 4 pi r squared. The charge enclosed, well, it's just all of it, so it's just Q over epsilon naught, and you get that same result we did for a metal sphere. KQ over r squared. Again, if you're Gaussian, if you're interested in the electric field outside an insulated sphere, it's the same as outside of a metal sphere, which is the same as a point charge. Okay, it doesn't matter if the charges are all on the outside, like metal, or they're evenly distributed throughout the volume, like an insulator. Insulator being a substance where the electrons aren't free to necessarily move. You just get a point charge, meaning the electric field is somehow proportional to R. Now, what about the inside? Okay, so there's my insulated sphere, and now I'm going to put my Gaussian surface on the inside of that. Okay, so I've only enclosed a fraction of the total charge. So if R is less than capital R, write down Gauss's law. Gauss's law says that the accumulation of E field over space is equal to the charge enclosed over epsilon naught. This is the flux, which is the number of field lines that are going to go through your surface, right? We're saying that the flux, all these field lines going through the surface, is proportional to the charge that you've enclosed. Okay, so electric field is constant on that Gaussian surface. The Gaussian surface has 4 pi little r squared, whatever the radius of your Gaussian surface is. And then here's the hard part. How much charge have you enclosed? Well, you've enclosed a fraction of the total charge. How much? Well, you've enclosed a certain volume, 4/3 pi r cubed. But if you look at that volume, meaning the volume of your red Gaussian surface, and divided it by the total volume, 4/3 big R cubed, and you multiply that, right? This is just a fraction. This is a ratio. This is a percentage. The percentage of the charge you've enclosed of the total is the same percentage of the volume that your sphere is taken up relative to the total sphere. Hopefully this makes sense, meaning if your red makes up half of the total of the blue, well then you enclosed half of the charge. Again, this gets out. Look how this will cancel really nice. Boom, 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 boom. This is E then equals, oh, sorry, boom. That's an r squared, and that's an r cubed, so we'll get rid of that. And so you're left with Q r, 4 pi epsilon naught becomes K, and then you're left with that r cubed. And what you can show here then is that the electric field grows like R, meaning it linearly grows. All the other E fields were decaying, right? 1 over R squared, 1 over R. The electric field in the sheet was constant. This electric field actually gets bigger as you move away. And so think of the graph here on an insulated sphere. Electric field as a function of R. When R equals 0, meaning you're at the very inside, well then the Gaussian surface can't enclose any charge, so it's got to be 0. And then the electric field grows, right? Constant, constant, constant. Little r is your variable. As your Gaussian surface gets bigger and bigger and bigger, it grows linearly until when? Well, until little r becomes big R. Once little r becomes big R, then you're on the outside. And once you're on the outside, then the electric field decays like 1 over r squared, which is then going to asymptotically approach 0. So this grows like r, and then this decays like 1 over r squared, and they love this graph. And again, these are the main kind of cases. Point, line, sheet, insulated sphere, and metal sphere. There are other examples that I'll do on the next video, but this certainly gets you started on Gauss's law. And again, Gauss's law just says that the flux, which is equal to this quantity, is proportional to the charge you've enclosed. The more charge you've enclosed, the more field lines should be going out. If the charge happens to be a negative charge, so put like a big negative charge here and then think about putting a Gaussian surface around it, then you have all these field lines coming this way. And so you'd have negative flux, which is okay. And there's nothing wrong with that, right? You're going to have field lines coming in or field lines going out. And again, if you know how many field lines are going in and out, then you should know what the charge is inside, because it has to be proportional to it. Again, if you think about a charge being outside, if this is your charge way over here and you have some Gaussian surface, well, that's not going to be affecting anything, because this is going to go in and it's going to go out. Okay, so that wouldn't add any actual flux to that particular thing. Okay.